Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to talk about mechanics, connected particles, part 2, stages. Now in part 1 we talked about the fact that now that we have connected particles, we have 2 net forces that we can work with. Well, in part 2 with stages, there's going to be something that happens in the system that changes the entire context. So for example, in our first question that we look at, the string is going to break partway through the motion. And so what is going on before the string breaking and then what proceeds to happen after the string breaking are 2 completely different stages of the problem. It's almost like having 2 problems wrapped up in one. So this is what we're covering today. Again, remember, mechanics is cumulative and we keep adding layers. The layers that we added with connected particles is our concept of tension, where we want to show the forces going inward or away from the objects, and also pulleys, which basically just changes the direction. Everything else that we've learned in the previous units still apply. So let's get right into it, and let's look at our first example here. Here we have the diagram. It says 2 particles, A and B, of masses 1.3 and 0.7 kilograms respectively, are connected by a light inextensible string which passes over a smooth fixed pulley. Particle A is 1.75 meters above the floor and particle B is 1 meter above the floor. The system is released from rest with the string taut and the particles move vertically. When the particles are at the same height, the string breaks. Show that before the string breaks that the magnitude of acceleration is 3 meters per second squared, and find the tension in the string. So we've seen this pairing of variables, acceleration and tension, before. And so we're basically doing the same thing, except we're finding the part before the string breaks. So let's go to our board and look at our diagram. I just put up the given information here, and then we need to fill in a few extra things. So here are the masses of particle A and B. Here's our pulley. A is 1.75 meters above the floor. B is 1 meter above the floor. And because we have a string attaching the 2 particles, connecting them together, we need to put our tension. So tension will be going upward here, and will also be going upward here. The T there like that. And we need to calculate our force due to gravity. So 1.3 times 10 gives 13 newtons, and 0.7 times 10 gives 7 newtons. Okay, so we put those in. Notice that the 13 is heavier weight from the 7. So when this is released, the A will go down and the B will go up. We also have a velocity, initial velocity of 0, because the system is at rest and then we let it go. So we have that to work with. And there's no inclined plane, there's no friction. So this is what we have to work with. So in part 1, they want us to show that A is 3, acceleration is 3 meters per second squared, and also find the value of the tension. So again, we're going to do this by using our net force, and the second Newton's second law, force equals mass times acceleration. So here we have mass 1.3 times acceleration. We cannot put in the 3 for acceleration because we have to show that a equals 3. Basically, we have to find the answer, but they've already given it to us. So 1.3a, mass times acceleration, that's Newton's law, equals the resultant of forces. Well, a wants to go down, so that's going to be 13 minus t. And then over here, we have 0.7a equals, and this one's going to be going up, so t minus 7. So here we go with this. If we solve for one of these, t equals 0.7a plus 7, we can plug that in up here. And when we plug that in up here, we get 1.3a equals 13 minus 0.7a plus 7. Make sure you put it in parentheses because that subtract needs to distribute. A lot of students forget to put parentheses and therefore they forget to distribute the negative. So this negative 0.7a we're going to add to the other side, and that will give us 2a equals 13 minus 7, which is 6. So we get a equals 3. And so that's our answer for that, which we've shown. Now we want to find the tension, so that's pretty easy. Just plug it right into here. T equals 0.7 times 3 plus 7. T equals, that would be 21 or 2.1. So 2.1 plus 7. So T will equal 9.1 newtons, and that is our tension. So that wasn't too bad. That was our first part of the problem, which we have seen in previous examples in video part 1. And that acceleration and tension combination in simultaneous equations is quite common. So this part was pretty normal. Now let's go on to the second part of the question. And this is where it gets interesting. Notice that the particles are at the same height when the string breaks. Find the difference in the times that it takes the particles to hit the ground. Find the difference in times for the particles to hit the ground. Well, let me clear some space and we'll get started on this next part. Okay, the first thing that I've done is I find that midway distance that we have when the string breaks to the ground here. So we have 1.75 meters and we have 1 meter. So halfway in between, if you add them up and divide by 2, you get 1.375. So as A comes down and reaches that point, B is going up. When they're both at the same height, this 1.375 meters, the string breaks. The moment the string breaks, we now have a different set of conditions. That's why I called this video stages. So stage 1, the string is attached and the particles are acting together. Now the string has broken, so each particle has to be dealt with individually, and tension is no longer a factor because the string has broken. So what we're looking for is time. So it's probably dealing with a Sekolah formula. We have distance, and we have what we want to find though is the velocity, because initial velocity is in every single one of those Sekolah formulas. So let's start by finding the initial velocity. And what I mean by initial velocity is the initial velocity from this point. So it's actually going to be the final velocity of the first stage will become our initial velocity of the second stage. So let's just call it final velocity of the first stage for right now. And to find that, we're going to use our v squared final velocity equals, and our initial velocity is 0, plus 2, acceleration we've already found. 3, I should have probably kept that information from before. There's our acceleration, 3, we solved that in the first part. And the distance. Well, the distance that we're looking at is from the 1.75 to the 1.375, or also from the 1 up to that middle level. And so to take 1.75 minus 1.375, or 1.375 minus 1, we get a distance that it traveled 0.375 meters before the string broke. So when we calculate this, our velocity is going to come out to, you can do the calculations, velocity comes out to 1.5 meters per second. So this is the final velocity of the first stage where the string is still intact. It's also going to be our initial velocity for the second stage when the string has already broken. So what we're looking for is time. We have distance, 1.375 for it to fall to the ground. And we have initial velocity, 1.5. Although I should point out that our initial velocity is going in the downward direction for particle A. It's going in the upward direction for particle B. So please pay attention to the direction. And I think that's all that we need. So distance, 1.375 equals initial velocity. Now this is for particle A. It's going, our orientation is from this line down to the ground. We're not using the ground as our point of orientation. We're using our initial velocity starting point. So since we are going away from that point of orientation, we are using positive 1.5 into the direction that we want to go, and that is down to the ground. So 1.5 t plus 1/2 a. Now a is not 3 anymore, so be very careful to rethink each one of your components in the different stage because the context has changed. Now that the string has broken, it is not bound to that system. The only thing acting on it now is gravity. So we need to use the acceleration due to gravity, which is going to be a positive 10 because the gravity is moving it in the direction towards the ground and away from our, starting point here. When we solve this, this is t squared. So we get 5t squared plus 1.5t minus 1.375 equals 0. Now you can just plug that directly in. We're not going to try to factor it. We're not going to try to simplify it. Just plug it directly into the quadratic formula. And when you plug it into the quadratic formula, you're going to get t equals 0.3954. So our time for A equals 0.3954 seconds. So what we want to look for is the difference between the times that it takes for the two objects to hit the ground. This is how fast it takes for object A to hit the ground. Now we move to object B. Actually, we can use the same formula. This is one of those situations that you can actually use. You can do it several different ways, but you can find yourself doing one or two equations when just one is enough. So make sure you're familiar with your SUVAT formulas. Have them right there in front of you so that you can select the more efficient way. We can use the same formula for particle B. So we're going to have, it's still going, it's still 1.375 meters away from the ground. That's the displacement at the point that the string broke. But instead of 1.5, we're going to use a negative 1.5 because it's going away from the direction that we want to go. We want the particle B to be on the ground, and right now it's still on its way up. So we're going to use a negative 1.5 t plus 1/2, and our gravity is working against our velocity. The gravity is taking us in the direction that we want to go. So we're going to make that positive because our point of orientation is this halfway point up here. It's not the ground. We want to go to the ground, but that is not our starting point of orientation. So t squared. And when we work this one out, we have 5t squared minus 1.5t minus 1.375 equals 0. Not a lot of difference, but the change in velocity or the change in direction of the velocity does make a difference. And so when we solve this, we get 0.6954. So t of b, time for b is 0.6954 seconds. And that does include the time it takes to go from 1.5 meters per second up to 0, because it's going to stop because gravity is pulling on it, and then come all the way back down. So because we used this formula, you don't have to double that time part. This is the entire trip for it going in that direction and then coming back down. So this is our entire trip. And so what we want is the difference in times. So time B, time B minus time A, 0.6954 minus 0.3954. Look, most of those numbers are the same. 4 minus 4, 5 minus 5, 9 minus 9, 0.6 minus 0.3 equals 0.3 seconds is the difference. Only 0.3 of a second is the difference between when those two objects will hit the ground. So let you see that there. I guess you couldn't see this one down here. And that's how we do this one. Again, notice we have a different stage because this is after the string is broken and you have to re-evaluate, for example, no more tension, acceleration has changed, what direction your velocity is going in, and so you have to recalculate almost all of your variables. It's like two different problems. Okay, now let's see if there was, I don't think there was a second part to that question. Nope, that's it there. So let me set up the next question for us. Okay, let's read our second question together. Here we have the diagram. It says two particles, P and Q, masses 0.3 kilograms and 0.2 kilograms respectively, are attached to the ends of a light extensible string. The string passes over a fixed smooth pulley, which is attached to the edge of a smooth plane. The plane is inclined at an angle of theta to the horizontal, where sine theta equals 3/5. P lies on the plane and Q hangs vertically below the pulley at a height of 0.8 meters above the floor. The string between P and the pulley is parallel to a line of greatest slope of the plane. P is released from rest and Q moves vertically downwards. So find the tension in the string and the magnitude of the acceleration of the particles, and it's worth 5 points. So again, let's look at our setup here. Here we have P and Q, here we have the masses. Notice instead of giving us the angle, it gives us sine theta equals 3/5. If you wanted to, you could calculate the angle, but you don't really need to, because when we resolve our forces, here we have 0.3. So this is going down here. That's 3 newtons. 0.3 times 10 is 3 newtons. And we want to resolve it perpendicular. So this is going to be 3 times sine theta, which is 3/5. So there's our 3 sine theta. And here we have gravity just going straight down. 0.2 times 10 is 2 newtons. And we also need to include our tension. So there's tension here. There's tension on that one. It's a smooth plane, so we don't have friction. It's moving from an initial velocity of 0. It's going to start with initial velocity of 0, and then it's going to move, meaning we have acceleration. And it wants us in the first part to find acceleration and tension. So by now, after video 1, part 1, and also now part 2, you can see this acceleration tension is occurring in almost every problem. So be ready for that. That should be your initial skill that you achieve, and then you can branch out to the different other questions that come with it. So again, we want Newton's second law, mass times acceleration. So we have 0.3 A equals, and it's going to go this direction. It says Q goes towards the floor. So T, that's all we have. We don't have a, oh, here we have this one right here. So we have T minus this 3 times 3/5, that's 3 sine theta there. And so that's 9/5. And we also have 0.2 A equals 2 minus the T, because this one is going to go down when it's released. And we have simultaneous equations here. So if we want, we can solve for T. T equals 2 minus 0.2 A. Plug that in up here. 0.3 A equals 2 minus 0.2 A minus 9/5. So if we add the 0.2 to the other side, that's 0.5 A equals, this would be 10/5. So 10/5 minus 9/5 is 1/5. This is 1/2. So A equals 1/5 divided by 1/2. Same thing as multiplying by 2 over 1. So our A equals 2/5 meters per second squared. So that's one part of our answer. And then we want to solve for our T. And our T, we'll just bring that back into right here. So our T equals 2 minus 0.2 times, and 2/5 is the same thing as 0.4, so we can do that. 2 minus, that's 0.2 times 0.4 is 0.08 for that, 0.08. 2 minus 0.08, our T then equals 1.92 newtons. So we have a tension of 1.92 newtons, and our A in decimal form would be 0.4 meters per second squared. And so there we have our tension and acceleration. And this should be pretty smooth. It's simultaneous equations. You can either use elimination or substitution, up to you. And this should be algebra that you're familiar with from IGCSE material even. And it shows up pretty much on every question. So that we've gotten through. Now let's see what happens in the next part. Moving forward, Q hits the floor and does not bounce. It is given that P does not reach the pulley in the subsequent motion. Find the time from the instant at which P is released for Q to reach the floor. Find the time from the instant at which P is released for Q to reach the floor. Okay, let me clear us some space. Okay, here we are. So we're looking for the time for Q to reach the floor after particle P has been released. Of course, the system is still attached by a string, so they're going to move together. And the distance that needs covered is 0.8. Since we're looking for time, time is one of the SUVAT variables. So when we look through our SUVAT and we have initial velocity and we want time, we've already found acceleration and we have distance. So we're going to use our, I want to keep our acceleration here. Our acceleration is 0.4, so I don't want to lose that. So what we want is our distance, 0.8, equals ut, our initial velocity, times time, which we're solving for, plus 1/2 acceleration, which was 0.4 t squared. So that gives us 0.8 equals, that's 0. Half of 0.4 is 0.2 t squared. So when you divide 8 by 2, we get 4. T squared equals 4. And when we square root, we obviously just want the positive time. So t equals 2 seconds is the amount of time that it takes for Q to hit the floor. So that wasn't too bad. That was just using our SUVAT. So in the first part, we used Newton's second law with net force. And in the second part, we used SUVAT. So let's go back and see, I think there's a third part to this question. When Q hits the floor, the string becomes slack. So this is where we get a change in the stage. Find the time from the instant at which P is released for the string to become taut again. Okay, so, let's think about what's going on here. This system moves. Q is going to come down and it's going to hit the floor and stop. That's 0.8 meters. This P will move up here, 0.8 meters. And when Q hits the ground, now all of a sudden the string doesn't break, but it's not moving forward anymore because Q has stopped. But P is still moving up the slope. So what we need to find is we need to find the velocity of P at the point Q hits the ground. So our starting velocity, we want to find final velocity. Final velocity for this segment right here. Our initial velocity is 0. So final equals our acceleration, which is 0.4 times time, which it takes 2 seconds. So velocity equals V equals U plus AT is what this formula is. Final velocity equals initial velocity plus the acceleration, which we calculated in the first part, times time, which we calculated in the second part, that it takes to reach the 0.8. And so our velocity is 0.8 meters per second, and that's this one right here. Now, once this hits the ground, the string is no longer tight. So we have a change in circumstances that we need to pay attention to. Tension is no longer acting, which means we need to recalculate our acceleration. So our acceleration during here to here was 0.4. Now we need to calculate a new acceleration. So mass, and we want to do particle P because Q is already stopped. So we're done with Q. We're working with particle P. So 0.3A equals, and now the only thing that we have, there's no tension because the string stopped moving once Q hit the ground. So there's no T. The only thing we have is this 9/5 here, and it's going to be a negative 9/5 because it is against our direction of motion. So when we take our negative 9/5 and divide by 0.3, we're going to get a new acceleration of a negative 6 meters per second squared. And notice it's negative because now our particle is not being dragged and it's going uphill, so it's slowing down because of the force of gravity that's been resolved parallel to the plane is pulling it back. But it's still going to continue on for a little bit of time. Now that we have our new acceleration, now we want to solve for how much time is it going to take before it gets to a velocity of 0, where it's going to stop. And then it's going to slide back until the string is tight again. Okay, so we need another velocity equation here. And this time our final velocity is going to be 0. We want our final velocity to be 0. Our initial velocity is 0.8 plus A is now a negative 6, our acceleration, and we're solving for time. So we get 6t equals 0.8, and when we solve for t, that's going to take us 0.133 seconds to get from here up to here, where P now stops because it has run out of velocity. And because this is a smooth plane, it's going to slide back down. And since the force sliding down is the same as the force acting against it as it was sliding up, all we have to do is multiply the time by 2 because it's the same force acting. So we get 0.266. And what we want is the time for the string to be tight again from the point of release. So we need to take our 2 seconds that we calculated in the first part, the time that it takes to hit the ground, plus this 0.266 seconds, the 0.133 going up and 1.33 going back, should be before the string is tight again, and then the string will stop it there. So 0.266 equals 2.2, and then of course the 6 rounds up the third number to 7. So we get 2.27 seconds from the time that P was released all the way up to and back again to where the string is now tight again. Okay, so that was our 0.2 for that, and I don't think there was another. That was already our part 3. So I will set up again for the next question. Okay, here's our third and last question for this video. And let's look at it. Here's our diagram, pulley again with objects. 2 particles, A and B, have masses m kilograms and km kilograms respectively, where k is greater than 1. The particles are attached to the ends of a light inextensible string. The string passes over a fixed smooth pulley and the particles hang vertically below it. Both particles are at a height of 0.81 meters above horizontal ground. The system is released from rest and particle B reaches the ground 0.9 seconds later. The particle A does not reach the pulley in its subsequent motion. So the first part of the question, find the value of K and show that the tension in the string before B reaches the ground is equal to 12 M, or 12 times the mass, newtons. And this is worth 7 points. So let's go back to our diagram and look and see what we got. Notice here's our mass, so we still need to calculate mass. So A is going to be down here at 10 m, so our mass times 10 m, and B is km times 10, so that's going to be 10 km for that. We also have a string, so we need to add in our tension. So tension going up on this side, tension going up on that side. So far, the strings that we've been dealing with are one string, so the tension is still the same. Don't have to label them, just T and T. And our distance, 0.81 high. So when this is released, it says K is greater than 1, meaning this mass is going to be heavier. It's going to pull B down, and A will go up, and it takes 0.9 seconds for B to reach the ground. But in our first part, it's asking basically for us to find the value of K and to show that the tension is equal to 12 m newtons. So let's start with setting up our net forces and Newton's second law. So mass times acceleration. So here is m times A is equal to, here, the T minus 10 m. Oh, sorry, we have, so we'll continue with this. M times A equals T minus 10 m. Over here we have K MA, let me switch to blue. KMA equal to, this one's going down, so 10 km minus T. Well, here we have 3 variables. We're looking for K, we're looking for T, we need to get rid of that acceleration. Okay, so we set it up, but we have 1 too many variables. So let's go ahead and look over here. Acceleration is not only in the Newton's law and net force, but it's also in suva. So let's see what information we have over here. This was released from rest, meaning this has an initial velocity of 0. We have 0.81 distance, and we have time. So let's see if we can find acceleration from there. 0.81 distance equals ut 0t plus 1/2 at squared. We have our t. Okay, and so our t was here 0.9. So we have 0.81 equals 0 times this, that goes away. 0.9 squared, and then divided by 2. So 0.9 squared is 0.81, divided by 2 is 0.405. And then now we can get our acceleration. 0.81 divided by the 0.405 equals 2. So our acceleration is 2. Now we can take that and bring it up here. So notice, I followed kind of the same pattern that we did with previous examples. And then I set up the Newton's law with the net force, the resultant of the forces. But this time, we need one more piece of information. So we go back, look, it's in suva. So we find the right equation that has what we need. We find acceleration. Now we can come back here and change this to a 2m. and we can change this to km. Now we can continue on because we got rid of the A. We want tension in terms of M. So now this is quite easy up here. Just add the 10M to the other side. So tension equals 12 M newtons. So that was part of it to show that tension is 12 M. And the second thing is we need to solve for K. So now we have 2 km equals 10 km minus 12m. And there's an m common to all of it. So if we divide out the m, then that leaves us with 2k equals 10k minus 12m. Add the 12m to the other side and subtract 2k. So we get 8k equals 12m. K equals, sorry, the m is gone. We divided it out. So we took out the m. 12 divided by 8, which is 3 halves. So our K equals 1.5. And so there's our second answer. So T, in terms of M and the value of K. So let's look at our second part of the problem. See what we have here. Now it says, at the instant when B reaches the ground, the string breaks. So here we have a completely different context, a different stage in our problem. Show that the speed of A when it reaches the ground is 5.97 meters per second. Correct to 3 significant figures. Find the time taken after the string breaks for A to reach the ground. So we need to find the speed of A and the time it takes for A to reach the ground. Let's go back to our board, and I'm going to need to clear some space. Okay, we're looking for both the speed of A when it hits the ground, as well as how much time it takes for A to get to the ground. So the first thing we want to do is we want to establish the velocity of A once B hit the ground and the string broke. So our velocity, final velocity, is what we're looking for. Our initial velocity is 0. And right now, since we're looking for the velocity at the point the string broke, we're still actually in the first stage. So our acceleration is still 2. We solved for acceleration in the previous part, and we got 2. So plus 2 times t, and our time that it takes for A to go up and B to go down is 0.9. So what we're looking for is the velocity up here when the string broke, and this will be at a point 1.62, twice the 0.81. That will be the height that we're at. So our velocity is 1.8 meters per second. Now, what we want to do is, now that we're up here at this level, we have 1.8. Our velocity is still going up. We're at a height of 1.62. Now we can solve for the time that it takes for our object to get to the ground. So we're at a distance of 1.62. Our initial speed, now that we're in the second stage, so this was at the end of the first stage, the final velocity, and now that the string is broken, it is the initial velocity for the second stage, that is after the string is broken. So 1.8 t, And it's positive because it's going away. We're going to use the ground as our point of reference. So it's going away from the ground. Okay, so I'm using the ground as the point of reference. Make sure you establish your point of reference because different people can choose a different point of reference and it will make your signs different. So as long as you're consistent with your point of reference. So if I use the ground as point of reference, the 1.8 is going away, so it's positive, plus 1/2. Now acceleration is due to gravity. We can't use the 2 anymore because this is now in the second stage after the string is broken. So now it's acceleration due to gravity, and it's going to be negative because it's bringing me back towards the origin t squared. So that gives us 5t squared when we divide and add it to the other side, minus 1.8t. And then this is already positive 1.62 equals 0. So there we have our quadratic. And when we solve this quadratic, just plug it into your quadratic formula. You're going to get t equals, you're going to get 2 values. Obviously, you don't want the negative one. So you're going to end up with t equals 0.777 seconds. So this is the first part of our answer, is the amount of time that it takes to get the ground. And now we want to look at the final velocity at which it hit the ground. And so our final velocity equals our initial velocity, and our initial velocity was the 1.8 going away. So v equals u plus at. Our acceleration is a negative 10, and our time is 0.777. So here's v equals u plus at, but this is stage 2 after the string is broken, and our initial velocity is the 1.8. And then when you solve this one, you end up with your final velocity being a negative 5.97. And a negative 5.97 means that it's 5.97 meters per second toward the ground. Again, I made ground as my reference point, so positive would be going away, negative is coming back toward the ground. We showed that the velocity is 5.97. So there we've got our second part to the question. So let's go back because there's a third part. So notice we were able to show that it reaches the ground with 5.97, and we also found the time, the 0.777. So the third part, sketch a velocity time graph for the motion of the particle A from the instant when the system is released until A reaches the ground. So we need to do a little velocity time graph. And again, I need to give us some space. Okay, let's draw this velocity time graph. So here we have velocity as a function of time, v of t. And here we have time. Notice I go down into the negative section because we had some negative velocity involved. So we have 2 axes here. We need to look for our key time, and we need to also look for our key velocities. Obviously, the first velocity would be our velocity when at the point of release, which would also be at time equals 0, and velocity equals 0. Then our velocity went up to 1.8 meters per second. So we'll just put it up here, 1.8 meters per second. And this is at the point at which the string broke, and that was at a time of 0.9 seconds. So here we have time in seconds. And then another 0.77 seconds later, so 0.9 plus our 0.77 is 1.677. So 1.677 seconds is when A hits the ground. Okay, so this is a velocity time graph, and our velocity of our A hit the ground with a negative 5.97. So this part represents it going away from the ground. This part is it's going back towards the ground until it hits the ground, and it's going to hit the ground. So here we have at 0.9, it reaches our 1.8. So remember, the slope is acceleration. The acceleration for that first part, I believe, was 2 meters per second. And so it was a constant velocity all the way until B hit the ground. A is now up here, and the string breaks, which means now A is now under the influence of gravity, and gravity starts pulling it back down, and it reaches the ground at this point here. And so obviously you'll see at some point in there, there is a point at which it's still going up, still has positive velocity, but the velocity is slowing down. It's a smaller velocity, but still positive. There'll be some point at which the velocity equals 0, and then it will start going back down, and as it goes down, it gains speed, and the velocity becomes more negative because it's going back towards the ground until it hits the ground. The point that hits the ground is at 1.677 seconds at a speed of a negative 5.97 meters per second. So we have our 2 key velocities, 3 if you want to include the 0 velocity, although we didn't calculate the exact time. We have 0.9 seconds that was given, plus the additional 0.77 seconds that we calculated to get a total of 1.677 seconds. This is really all that you need. Key velocities, key times, velocity time graph. And so that concludes our connected particles part 2 in stages, where you have to account for what happens, like when the string breaks, because you have to recalculate acceleration and your tension disappears. You're now under the acceleration due to gravity or something like that. So it makes the question more challenging, so break it up into the stages. Remember, your final velocity of stage 1 just might be your initial velocity for stage 2. Again, thank you for joining me in the Zoom room, and hope to see you again next time.